Counting without counting, the fundamental counting principle. In this presentation, you will learn how to define the fundamental counting principle used to solve one of the basic problems of combinatorics of finding the number of possible configurations, be they arrangements or formations of objects of a given type or set. To start with, we need to understand what is combinatorics. Combinatorics is a field of mathematics concerned with problems of selection, arrangement, and operation within a finite or discrete system. Its objective is how to count without counting. For example, how many integers are there from 3 to 11 inclusive? One learner would say there are 8 integers, that is 11 minus 3. Is this correct? Let's check by listing all these integers and physically count them. That is 3, 4, up to 11. Then we count them, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 integers from 3 to 11 inclusive. Therefore, the correct way of counting without counting is 11 minus 3 plus 1 is equals to 9. Also, we need to remember that determining the probability of an event often is a counting problem. That is to say, in finite probability theory, we need to know how many outcomes there would be for a particular event, and we need to know the total number of outcomes in the sample space. But often the numbers are just too large to count in the 1, 2, 3, 4 ordinary ways. Therefore, one of the basic problems of combinatorics is to determine the number of possible configurations of objects of a given type or set using the fundamental counting principle. But why fundamental counting principle? The fundamental counting principle provides us with a simple way to determine how many ways we can arrange items in a given set. So it's about arranging items in a given set. That is what the fundamental counting principle provides us. In this regard, the factorial notation, a mathematical expression, is used to indicate the number of ways to arrange a data set with a specific number of values or elements. The factorial notation uses an exclamation mark. For instance, 5 factorial is a way of arranging a data set with 5 values or elements in it. That is to say, 5 factorial is equal to 5 times 4 times 3 times 2 times 1, which is equals to 120. Meaning we can arrange a data set with 5 values in it in 120 ways. In general, n factorial is equal to n times n minus 1 times n minus 2, and so on up to 1. If you compare this expression and this one, my n in this case is 5. So we are saying 5 times, that means from 5 we subtract 1, then we get 4. From 4 we subtract 1, then we get 3, and so on until we get 1. So that is the same thing that is happening here. N times n minus 1. To n minus 1, we subtract 1, we get n minus 2. To n minus 2, we subtract 1, we get n minus 3, and so on until we reach 1. Again, we have 0 factorial, which is equals to 1. 0 factorial is a way of arranging a data set with no values in it. That means the data set is an empty set, right? So by definition, a 0 factorial is equal to 1, just as 1 factorial is equal to 1, because there is only a single possible arrangement of this data set with 1 value. So if we have a data set with only 1 element and an empty set, we are simply saying the ways we can arrange an empty set is only one way, because we'll get an empty set. The ways we can arrange a set with only 1 element, we can only arrange it as 1 element. This is why 1 factorial is equals to 1. 0 factorial is equals to 1, meaning 0 factorial is equals to 1 factorial is equals to 1. Note that in combinatorics, you will encounter very long multiplications of numbers, and the factorial notation is a simpler way of writing those long multiplications. Let us now define the fundamental counting principle. I have this example 1. A coin is tossed and a die is thrown. The table below represents the possible outcomes. That is the sample space represented by S. Right? Here is my die. As you can see here in the picture, that's a die. It has 6 sides, right? And the sides with the dots is from 1 up to 6. For example, this one you can see, so this represents 4, right? So that's the die for you. Then we have a coin. On a coin, you can have a head and a tail. As you can see, that is a coin. Therefore, we are saying now, that said, we want to write down the possible outcomes. That is, if on the die, I have a 1, then I have to imagine what could have come on the coin. So if I say we got a head, then I say H1. Or if we say we got a tail, then it's what? T1. I can go to 3. Suppose on the die it was a 3, right? So on the coin, it could have been a head, then it's H3. It could have been a tail, then it's T3. This is how we are getting the possible outcomes. And these are the possible combinations as far as a coin and a die is concerned. Now, if these are the possible outcomes, right, we are saying, what is the number of these possible outcomes? So we can actually physically count them and see how many they are. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. They are 12, right? So the answer is the number of elements in set S, which is the sample space, which is represented here in the table, is equals to 12, right? Now, the question is there a way of counting these without listing them? That is, we are not supposed to have this table. All what we needed to know is we have a coin which we are tossing and a die which we are throwing. Then we ask ourselves, what is the number of possible outcomes? So without writing this table, do we have a way of knowing that? The answer is in the fundamental counting principle, which simply states that if there are m ways to do one thing and n ways to do the other thing, then there are m times n ways to do both things. I want you to understand carefully here when we say m ways and n ways. The ways are simply like the possible outcomes, right? What are the possible outcomes? Suppose if I throw a die. So those are being represented as the ways of doing one thing, right? The same can be said now, what are the possible outcomes if I throw a die? I can get a 1, a 2, a 3, up to 6. Those are the possible outcomes that can come out. So at the end of the day, what is key here is to understand when you talk of M ways of doing one thing and N ways of doing the other. The ways are like possible outcomes, things that we can expect, right? So in the example, when tossing a coin, there are 2 possible outcomes. Those are the number of ways we can do the throwing of a coin, right? When rolling a die, there are 6 possible outcomes. That is, those are the number of ways we can associate with throwing a die, right? Therefore, there are 2 times 6, which is equals to 12 possible ways of doing both, which is the sample space. So once you get it from here, then as we go forward, we can be referring to the number of ways, looking at the possibility sets, right? So at the end, when we say what is the number of possible outcomes, we are looking at the possible ways of doing the activity of throwing a coin and a die, right? So this is what is important about this. We shall see what happens as we go forward, as I keep on explaining and making sure that you don't confuse the word ways and possibility. That is the probable space.